All right, let's start.
Great. So thank you everyone for joining this session. Please mute yourself first. When you have questions, please raise your hand and I will call you according to the order. You are encouraged to switch on your video to increase the participation. And first 5 minutes, let's give Edwige uninterrupted presentation. And we are very happy to have Edwige from Washington University in St. Louis talking about using machine learning to measure conservatism. Okay, it's all yours.
Thanks, Millet, for the introduction, and thank you so much for all the organizers, in particular IUN, to have invited us to present this machine learning project using machine learning to measure conservatism. It's co-authored with Jeremy, Yifei, and Mario. So Mario is here today and is really our machine learning expert. So I will clearly defer all the very technical questions, if we have a couple of them, to Mario, if times come about those technical questions. In any case, this project is using machine learning to an accounting research measure. This conservatism measure about differential timeliness. So beyond the aspect that, yes, we are going to apply machine learning to, oh my God, sorry, I had missed a slide, to measure, to construct an accounting measure with conservatism, you can obviously think about this approach to be applied beyond, of course, the measure that I'm going to present. Clearly, from there, the advantage of those machine learning algorithms is obviously to extract patterns from large data sets, and you don't have to import any functional forms. So you can take into account many nonlinear combinations between variables, and it might be very important. However, in terms of this project, we are not applying machine learning to predict a pattern. We will use in this project machine learning to filter out noise in measures. So the paper in question is implementing a neural network method to build a machine learning measure of differential timeliness based on Basu and Ken and Watts. So we will build on their approach. So we don't plan to address the critiques that have been brought up in the past about those Basu coefficients and so on, but we will show you how you can use machine learning to denoise, I would say, this machine learning measure. In any case, at the end of the day, we will show you that the measure that we are offering is using more information and is able to reduce noise, which is a problem, especially when you run operations and you want to use as is this notion of a differential timeliness. When you do that, you will see that in our approach, you will be able to get our measure and literally to put it in your regression if you have a specific question in mind that requires a variable measuring conservatism. With machine learning, we don't specify any functional form, so it's non-parametric in this sense. And you will see down the road that the non-linearities seem to play a role in explaining this differential timeliness. From there, what we were saying, we will have enough variation to use as is in a test, because if you look at a typical linear combination in a regression, you cannot use as is those measures. So typically the way people will then try to fix the issue is separately yearly regressions so that they can get this conservatism measure, okay? But the problem by doing that, and I will show you that in this presentation, is that this measure, those linear constructs, they are pretty unstable, okay? And it seems to be driven by capturing, I would say, the yearly shocks. At the end, I will show you that thanks to this neural network method, we will be able to filter out the noise. And from there also, the advantage of this method is to add restrictions that make economic sense. So as a restriction, we think it's important to think that on average, we have actually a co-movement between earnings and returns. And when we will apply the neural network method, we will impose those restrictions, so the positive correlation between earnings and news. By the way, if you are interested in getting our machine learning construct of differential timeliness, it is publicly available. We have actually, you have an open source file that is available. So you have the reference right there and also in our paper if you are interested. So the results, our machine learning measure is exhibiting actually a better fit of differential timeliness. We fix economically anomalous observations. You will see how in the presentation. It seems to be relatively stable because you will see the other linear constructs, they looked pretty unstable. And then with some tests to kind of sanity checks to validate somehow this measure. So first, this measure seems to be consistent with some associations that have been documented in the previous literature. And then we will also run some simulations to have a sense whether our machine learning construct is performing relatively well, even if the true data generating process is not coming from this machine learning model. So at the end, our measure seems to be quite robust to misspecification. So there is a relatively nascent literature in accounting in terms of how to apply machine learning method. So you have a couple of papers out there that use those algorithms, but on different topics. And of course, in terms of the conservatism literature, those are linear regressions. We build on this approach, but we will use instead machine learning. So just as a reminder, but I think most of you know what we are going to talk about in terms of differential timeliness. This is this graph. And on this graph, you observe that there is a stronger reaction of earnings to bad news. So earnings tend to be more negative when the news is bad. So you have this structural break around the favorable news. And this is what we refer to as the differential timeliness. At the end, you test this structural break by regressing the earnings on returns with an interaction that comes in the form of an indicator variable for negative returns, that is to say, bad news. In any case, this is here the Basu approach. That was the first paper that started this literature. So you have this regression, the X, those are the earnings. And then on the right-hand side, yes, you have the returns and the DOMI variable that I was referring to. The coefficients of interest here are constant. So here, the way it is done with the Basu is just a pool time series regression. And in this context, the beta 2 and beta 3, they are constant. So they are not really useful then if you want to use, obviously, this measure in another type of framework. And we will care about the beta 3, which is measuring the degree of conservatism. So this is the C that we will refer to down the road. And beta 2 is the timeliness of good news. So typically people refer to it as G, okay? So beta 2 is in front of the return, and beta 3 is the coefficient that is estimated with the DOMI variable for bad news. In any case, then we got obviously a lot of other papers that followed this approach. Here I present the Canaan Watts, and inside the Canaan Watts is the same type of regression, but this time there are other firm characteristics that are included. The firm characteristics in questions, those are the Ys. So it's a vector of 3 variables, the size, the market to book, and the leverage. And this time, the betas, they are functions of those 3 firm characteristics: size, market to book, and leverage. Of course, they are referring to the same interpretation. The G is the timeliness of good news, and the C, the degree of conservatism. So you cannot use, obviously, this regression as is. And the way then, because then, you know, the construct is a linear combination, obviously, of the firm characteristics. And if you use it like that in a regression that has the same controls, it is creating this problem of collinearity. So then people, do they fix that? Typically, they would run this regression by subsamples, typically using separate yearly regressions, okay? But I will show you that if you run those regressions by year, it looks pretty unstable. So in this graph, what do we have? We have actually the coefficients, and I need to insist on that. You see, the coefficients that basically aggregated will lead to the to the C-score, and every single coefficient is pretty unstable. You see that we have huge spikes, ups and downs everywhere in this time series. So the market to book is around like 0, but with positive and negative values. And then if you look at the size, which is like the black line, and the grayish line for leverage, the spikes are even bigger, like many folds, like bigger in terms of the positive and negative values. So it shows a lot of instability, and it's raising maybe the question that why do we have actually so much variation? Okay. Now, if I flip to the second graph, here we represent actually the C-score. And again, you see, we have huge spikes in this time series, and it might be maybe a problem. It seems actually to be driven by the yearly shocks, okay? And well, we will show you how actually the machine learning measure can give us a more stable measure. In any case, we move also to something that is raising some questions when you look at the Canaan Watts approach model. So if you look at the distribution of those basically of the G-score, and then you look at the G plus C-score, here is what you notice. So the G values, they should be actually positive. And what is kind of striking here is that about half of the G values are negative. So that is not as bad for basically the G plus C distribution that is representing the bad news. So the G density, it was for the good news, and the G plus C, the bad news. So for the bad news, again, we should also have positive values, but we have still about a quarter of G plus C values that are negative. So we should obviously observe rather movements between earnings and news, and already that's not really the case. Ayun.
Yeah, so I think that the literature kind of like know this negative correlation between earnings in ERT and returning ERT, right? And then I think that is mainly driven by those young NASDAQ firms after companies that start adding them after the 90s, R&D, other investments in the early stage firm will actually have negative correlation with the expectation of future positive cash flow, right? So I think I saw your footnote 1 that you kind of impose there will be a positive, but like it sounds like there's a reasonable economic explanation for the negative correlation between the contemporaneous earnings and returns. Then why do you want to enforce all of them?
So Ayun, I agree with your explanation. We obviously put it also in the paper. We agree that is actually especially true also nowadays with the digital companies.
Yeah.
Okay. But we thought that still it was those are more exceptions than the rule. Okay. However, right now what we are doing, and we are currently running this algorithm of neural network by not imposing anything.
Yeah.
Okay. So we are also doing that. So Mario, do we have the results yet? I don't think so.
Not yet.
Not yet. Okay. Just didn't want to say something that was not true.
Yeah.
So we are doing that, and we will see whether it's fundamentally actually changing the outcomes. Sounds good? But yes.
I think what will be more interesting is that I think you kind of like pull all the firms into kind of like testing sample versus out of sample, right? Would it be interesting to actually have 2 testing sample, because actually they are very different kind of firms in terms of their
I think it's a good
life
suggestion
cycle.
that maybe also we should look at those very specific firms, the digital firms and so on, the young firms. Yes, maybe it's something also
you can look at. Charlie has a new paper, right? Not a new paper anymore, but about like new economy firms and declining earnings returns relation that potentially I thought would be correlated with your declining conditional conservatism. Just the first order effect is declining, so the interaction term will naturally decline.
Okay. So thanks. So from there, this approach with the machine learning. So here we will use the same spirit as what we were looking at in terms of we have the earnings, the X that are equal to a bunch of variables, same thing as before. The only twist that we have is that we will not impose any functional form for the G and C function. So in other words, we can take into account the nonlinearities between the variables and see whether they matter. So this estimation is non-parametric in this sense. And what I also wanted to emphasize, and so here that is on the slide for the time being, Ayun, yes, we impose for the time being the positive constraint because we think, yes, we understand that we can rationalize for young firms and digital firms this potential negative correlation, but that should not be the norm. Okay, so in any case, from there, we will use the neural network to get this M, this function that is a function of the vector of firm characteristics and the returns. So, big picture about how this method works with the neural networks. So we have 3 categories of inputs, and from those inputs, we need to go to this output once more, this M. You see, it's right there. Okay, so the way those inputs work. So we have the most action with the Y's, that is to say the firm characteristics. In our approach, we will not only use the Ken and Watts firm characteristics, we will also derive the machine learning construct using more variables. In any case, those are those Y's. Those are the inputs. Then the bold arrows are representing vectors, because those, so this is a vector of input that is feeding here those embedded networks. So those embedded networks, at the end of the day, they will estimate a function that we care about. So the functions at the end that we estimate, this is F, G. So of course, we mentioned that before, but G now is estimated with the machine learning method. Same thing for G plus C and then D. From there, you have also the other inputs, so the returns and the do me, and they will go to this step right there, where we will eventually aggregate, I would say, everything to get this M, and then we will be able to give you this machine learning construct. In any case, here is the data selection. So it's a long time series. We start in 1963 to 2019. We get the data from CRISP and CompuStat. Yes, Ayun?
So can we go back to the neural network?
Yes.
This is kind of like the thing I don't really understand due to my lack of knowledge of ML. It's like, I think in the prediction exercise, we know that there's a truth, right? Will be either stock return tomorrow or weather tomorrow. So that's actually how we pick which model or which function will performs well. I think here, like, accounting conservatism is something we don't really know the truth. So when you are saying you are feeding better, is that feeding better with stock return in the same period? What exactly is your proxy for the
when we so when we will go to the fit aspect of it, we will have a measure of R square. So the fit is measured by the R square. Okay. And yes, you are right, because I didn't want to go to all those details, but yes, you have a training sample and a test sample. So you have an in-sample fit and an out-sample fit. Okay. So yes, Mario, you wanted to add something.
Mario, do you want to add something?
Yeah. So basically, so you're right. We don't know conservatism. We only we feed the earnings. Okay. So you see the X in the variables. This is the earnings. So we feed the whole functions, the whole function M with embedded F, G, G plus C and D. And after this is trained and we feed the earning, we extract these functions to compute the C-score. Right, so there is a two-step of we feed the earning, we don't know the C-score, and then once we have fitted the different functions, then we can easily extract them and compute the C-score.
Okay, so the exercise is like using either earnings. So we want to predict earnings, and then we are going to use ERT return or some of the characteristics of the firm from ERT or the previous years. Okay.
So to some extent, when you think about the fit, even if it's machine learning, this is the same way you would think about fit for regression. You see what I mean?
Yeah.
Because at the end, you want to fit what is on the left-hand side. And then, of course, we will speak about the construct itself, which is not, I would say, the model, but just the construct, which is inside one of the parameters on the right-hand side of the equation that we were looking at. From there, we have effectively two sets of big variables. We have the common three variables that are used in Can and Watts: size, market to book, and leverage. And then we augment that eventually with 5 more variables: volatility, age, cash flow, accruals, investment cycle. Of course, we would have liked maybe to look at more variables, but there is a trade-off. We need actually also variables where we have a lot of observations. Otherwise, we might have an empirical issue as well. So in any case, we have also other variables that we had taken in the past, but they were not as populated, like bid-ask spread, like there was another one, the PIN, and so on. So in any case, we will actually run different models. So we have 4 different models. We have the first one, which is the typical pooled OLS. Okay, so you can think basically BASU. Then we have the yearly OLS. You can think Can and Watts. And then we have the machine learning method, so the neural network that will be applied, but where we don't have the year fixed effect. And then we have a second neural network with year fixed effect, if it makes sense. So as we were saying in the past, in this version at least, we only have the results where we impose the positive constraints on G and G plus C, okay? Now, here is all the comparisons that we will be able to do down the road with all the models that we are estimating. So a lot of things going on here. So here you have just the linear models versus the machine learning models. So one way to compare those variables at the end, those models, sorry, you have here L1 and L1Y. So for the linear models, when you think L1, you should just associate that with the 3 variables only, okay? And then the Y is only indicating the fact that we take into account the yearly shocks, okay? Now, going to the machine learning, this is the same spirit, except that this time here, okay, so year, Y is standing for year, but this time, of course, it's not a linear model. Okay, so here we will see the effect of non-linearities if it matters. So comparing that to that. Then here we augment the number of variables by adding 5 new variables. In this case, we will refer to those models by calling them 2. You see, you have the digit 2, it just means more variables. Of course, if we have the Y, it only means that we have also the effect of yearly shocks. And same thing as before, if you go from here to here, so linear models to machine learning models, it's only capturing the effect of non-linearities. So of course, there are a lot of ways to compare then all those models. We will see down the road what we can discover. In any case, so Ayun, that goes back to your fifth question. We start actually with that. And here we report this R square for the different models, okay? In this case, what do we notice? So a lot of information going on. So let me highlight a couple of things. So when we compare this linear model to the machine learning model, only looking at the Can and Watts variables, you see that actually the fit of the linear model is slightly bigger compared to the machine learning model, but the machine learning model does not take into account the time effects, and still it can achieve almost the same fit. And if we compare only the 2 linear models, that is to say the one without the time effects versus the one with the time effect, we notice that clearly the fit is increasing like crazy, plus 114%, which is a sign that those yearly shocks, they helped the fit. But it seems from the previous remark that those maybe yearly shocks, they are actually coming from non-linearities, because as you can tell, this machine learning model has almost the same fit, and of course doesn't take into account the time effects, but indeed takes into account potential non-linearities. So from there, now, if you compare within the machine learning models the effect of time, you notice that, yes, you do increase the fit of the machine learning model that is taking into account the yearly shocks, but is not that big compared to the linear models. It's only an increase by 43%, whereas before it was much higher. Now, if we go to the effect of the additional variables, and we compare the machine learning model a la Can and Watts versus the new one where we add more variables, clearly we have a much higher fit by introducing those new variables. You can tell it's more than doubled thanks to the new variables. So now, if we look at the comparison between the linear model that is taking into account the effect of the time and the effect of the additional variables, we notice that now our machine learning model that does not take into account the time effects is returning a much higher fit. You see, 0.45, whereas for the linear model, it's only 0.40. So clearly, it seems that those early shocks, of course, because the linear model cannot take into account the non-linearities, this linear model, by introducing the early shocks, it was a substitute for the non-linearities. It's what I wanted to emphasize once more. So now, again, we want to highlight the importance of non-linearities versus time effects. And clearly, those additional variables, they also play a role to improve the fit. Ayun.
Yeah, so I kind of like want to go back to the earlier kind of like discussion, the quick question I had before is that I thought that the literature, at least in the empirical literature, as empiricists, we struggle that whether the Basu coefficient really captures the differential kind of like thresholds accountants actually use to report two different types of news, right? From the beginning of your paper, there's a different level of uncertainty or threshold. Kind of like we want to capture that, but like I think as empiricists, we are really not sure that the Basu OLS regression really kind of capture that. But I kind of still struggle to see how does this R-squared comparison exercise really kind of like get us at whether you are capturing what accountants actually internally within the firm reporting those numbers by exercising conservative measurement rules.
So at the end, I think, so what I want to emphasize first is that clearly our approach doesn't address the conceptual, I would say, critiques that are coming from this literature. So that we cannot address. And I think to some extent, your question is coming from there, okay? Yeah. So here we have, I would say, the same limitations, okay? So that's not resolving that. However, what we offer is clearly a way to use a new method in the field of accounting to address those questions of measurement. So maybe you don't like, let's say, this notion of conservatism, which is fine, you see what I mean? But clearly, as you can see, and there is a lot of instability in the coefficients, as we were saying before, and you will see down the road in a later graph that we can get a construct that at least is more stable. So it's a sign that this machine learning is helpful for a measurement purpose. Steve, you wanted to add something. I know that you love, of course, the Basu coefficients.
I just want to add to what Young said. You know, I have trouble with this whole literature.
I know.
You know, if you get a Basu coefficient and you go to the 10K or the 10Q, you ask, can I see it? I can't see it, okay? So if you can't see it, you can't see it. If you get this Watson-Kahn thing, you know, size, that covers a multitude of sins. Market the book is more unconditional conservatism. Leverage, I mean, it's all sort of, we're all off in fairyland, it seems to me. If you can tell me this help, I can actually find asymmetric timeless and see it in the 10K from my analysis, that's one thing, but actually I cannot. So this is not a criticism, of course, of what you're doing, and I'm interested in your application of machine learning because I want to learn about that. But I just wonder whether you got the wrong target. I actually think this is all out to lunch. We're often fairyland, pretending we have this academic idea of asymmetric timeless, and we have these arbitrary regressions to pick them up. It's just a beta coefficient on a reverse regression. So I have a lot of reservations. Now again, and this is a tangential comment, perhaps, but it's not a criticism of your paper, and I'm interested in seeing what you're doing here. But
I cannot say the contrary, Steve. We cannot address all the critiques that you are obviously mentioning that have been brought up, because that's not basically our goal here. So I know that you're not clearly a fan of the, Basu and Ken Watt's literature. So the way to think about our paper, and you understood our obviously goal, is at the end, how to use this machine learning to address measurement problems. So yes, of course, if you don't like then this conservatism literature, you should think, okay, but let me then offer another setting where we could use machine learning. So that would be, I would say, another project. But here that would be the same approach to apply what I am going to present. Okay.
Yes. Okay. That's fair enough. I mean, it's a question of a choice of setting where you're actually getting some real identification that's going to help me to understand
how you can use this neural network
I can use
method.
It. Yes, that's right. Yeah.
But clearly, we cannot solve the conservatism debates. No, we would love to do that, but that's not the approach here. We just hope.
I don't think there's a conservatism debate. I mean, we understand conditional conservatism, unconditional conservatism.
We cannot address that here.
The issue is just whether you're actually picking up anything by these methodologies with these Kahn and Watt's C-score. The thing is, this is an academic deal. There's no validation. Okay. So what you get and what they get, there is no validation that you're actually picking up something.
I would say, maybe I will not convince you, but let's put it this way. In the follow-up slides, I will show you at least a way to get at this validation idea, not for the conceptual idea maybe per se of conservatism, but show you how at least the machine learning construct performs better over those other models. Because
yes,
clearly,
if it's, I'll look forward to that. If it's saying, I actually pick up better projections from these coefficients, okay. But the question what those coefficients are picking up. Okay.
Yeah. So Ayun, yes, go ahead.
I think in terms of how you position the paper, would it be easier for you to say, hey, we are going to use ML to understand determinants of earnings? Similar to kind of Peter's paper 2 weeks ago, and we are going to use some nuanced technology to predict future earnings, and conservatism or whatever, this asymmetric behavior will be one of the determinant, right? Because I think going back to Steve's point, like you can never really validate. But the exercise here is that, back to Mario's response, is that you are just feeding current period of earnings.
So we will obviously fit the earnings at the end. It's what I was showing you in those slides right now. We need to think more about it, I think, for the writing, let's say. Yes, Pengro.
Yeah. Are these additional variables selected by you or machine? Because if you selected by you, so what's the rationale for that? I know you can and would, because they choose a side, book to market and leverage. Basically, they use this to measure risk. If you think about the reverse price return related to this risk, so we can know what's the rationale behind those few variables.
So when we
have your additional variable, you choose this additional variable, or the machine selected that for you?
In terms of those 5 additional variables that have been introduced in the model, this is coming from our choice, but they are picked according to the literature, because some people have basically provided some reasonings why they could matter to explain the differential timeliness. So we have again this notion of risk that you were mentioning, inside volatility, and then the others, they have been also documented to be related to a measure of differential timeliness. But even though we have selected to start with those 5 additional variables, the machine learning method will tell us actually whether it plays a role. That's the reason why then I show you whether it has an effect in terms of the fit. Okay. However, Mario, can we say more about the importance of each variable per se? You know,
Yes,
we don't have that right now in the paper, as far as I remember, which is, I think, Penguo paper. You know, I know in the preceding project we had, which was a very different thing. We had the importance of each variable, and we didn't get at that whatsoever in this project.
No, we didn't do it yet, but you know, that could be done. If this is something that people are interested in.
Okay.
Thank you.
So, thanks. So now, so Ayun, and also to so going back to your one of your questions. So yes, we were noticing before, if you remember, in the linear models, well, it was super stable, and clearly it was raising then maybe questions. And when we use now our machine learning model, and we want to push a special model, which is this MLC2. So MLC2, we don't have the time effects whatsoever. And we notice that in this instance, when we report in time series the C-score, well, there is this declining trend. And before we had like no pattern whatsoever. So maybe this decrease in conservatism is aligned with the way the FASB has thought about the conservatism over the years, because even in terms of the terminology, nowadays, we don't necessarily speak about conservatism anymore, but rather prudence. So conservatism doesn't seem to be so important anymore. And we have this decline here. Ayun.
So like, is there any kind of rationale to explain this declining trend? Because you think about like the accounting rules from moving from pooling to purchase accounting for M&A after 2000, we would expect to see a lot more goodwill impairment, right? And according to Sudeepa Basu's kind of latest paper, most of the conditional conservatism he intended to capture will be asset impairments and a goodwill impairment in terms of dollar amount.
So you would have predicted the opposite then.
Yeah, so I look at the trend, and then I expect to see after around 2000 start kind of picking up, because previously you amortize,
so
and then later on.
So my little, you know, my little comment about that, in my case, I was like thinking, if you look at the conceptual framework that we have, that was done like a couple of years ago between the FASB and the ESB, they don't speak about conservatism anymore, but they use rather the term prudence. So to some extent, I think even the word itself, prudence, you see, is not again as conservative. And I think there is still this notion that also the firms over the years, they don't seem to have been maybe so conservative. At least this is what we see here. But you're right, with the arguments that you are pushing forward here, that some of them could have triggered the opposite reaction. So at the end, we have this.
You can run. Yeah, one thing you can run right now. You use the bottom line, net income, right? Use the operating income to see whether the trend is similar. Somehow those very asymmetric differences were kind of like, or between the operating income and net income, those kind of like restructuring.
Okay, so whether to see how it is related. Okay, so we take a note. Okay, so we will do that. So I think at the end here for this graph, at least it's not like, you know, there is a kind of trend. That was the first takeaway we wanted to emphasize. And there was no reason to get a trend. Let's put it this way. Now, here, to be honest, in the new versions, we don't know whether we are going to keep those analyses, but let me show you how we are thinking about them. So we wanted to have some sanity checks to see whether the measure that we were getting from machine learning was not picking up something that was completely inconsistent with what people had in mind. And it seems to be the case that all the relations with those economic variables, they are in line with what the literature has documented. So in other words, here you have a negative relationship between size and our C-score. Okay, yes, it's convex for our machine learning construct. Okay, same thing for leverage, mostly the same, I would say, yes, with a couple of differences, especially you see like at the tails right there. Okay, same. The only difference that we truly observe is for age. So actually, we go back to your question, you see, Ayun, with the young firm versus old firm. So maybe there is something more to do. So maybe we should target a specific analysis towards that. But clearly, the machine learning construct doesn't pick up the same thing relatively to the linear models in terms of age. Okay, so it's inversely U-shaped for the machine learning, whereas it's just more like a negative relationship for the linear models. Okay, so to be honest, it's like everything here. We can maybe find like consistent stories to explain, this pattern, but it doesn't mean that it's truly the explanation. You see what I mean? So in any case, the takeaways here is that mostly our machine learning construct seems to be aligned with what people have in mind when they correlate a differential timeliness measure with another economic variable. So now I think this is the interesting part here. At least when we were doing this part myself, I was really excited because I thought, oh, that is cool. It's really for me the true way, if there is a way to get at something more about validating a measure, is by doing those simulations. So those simulations, what is the spirit once more? Of course, we don't know the true data generating process for conservatism. Okay, the only thing that we can do is that we can assume that, okay, if the true data generating process is coming from a linear model, how would our machine learning construct work? Okay, perform. And same thing for the linear models. If basically we use instead the linear models on a true data generating process that is coming from machine learning, how do they perform? And of course, we control that in those simulations. And in any case, so we simulate earnings and so on. We need then to assess whether at the end our construct of machine learning works well. And to do that, we need a notion of error. The error that we look at is the mean absolute error between the true C-score that is coming from the true data generating process that we control. We are like, designing those simulations that way, and the estimated one. And we look at the difference, okay? So in absolute terms. And again, a lot of information going on right there, okay? So here, how to read this table. Let me show you one thing. We focus on this row here, which is about the machine learning construct that we want to push, MLC2. And in MLC2, we see that actually it's performing relatively well, when we simulate all the true generating process coming from here, linear models, machine learning, and then again linear and so on. In any case, we see that, the errors are not so large, and you will see why. Because if, for instance, if you look at the machine learning construct performance, if the true data generating process is a linear model with the yearly effects, the error is only 50% of the L1Y standard deviation. However, hold on. If you look at the performance of the linear construct, clearly error is much, 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 much larger. It's 500% of the machine learning MLC2 standard deviation. So if the true data generating process is coming from this MLC2 model, then the linear construct is really not that great, is not performing well. That's the idea. So again, you see that machine learning helps in terms of this measurement problem, filtering out the noise. So then we have a second type of simulation, and we think it's important for future work. So this is why machine learning can help us then to do more work down the road by denoising some measures. And the way to assess that is that we will simulate an object of interest, which is this ZY. And here on the right-hand side, we will care about this alpha. So in the, we know that this alpha, the true estimation should be equal to 3, okay? And we will see the different models are able to recover correctly or not this alpha equal to 3. And here is what we see. Again, a lot of information going on. Let me focus on one thing. So the machine learning construct, well, it's not perfect in the sense that it doesn't recover in all the specifications the alpha equal to 3, but at least this alpha is positive regardless of the data generating process, which is not the case for the linear construct. If you look at the linear construct, it can even return a negative alpha, which are signs that clearly the performance is not great whatsoever if you use it in a test. Okay. So this is actually the conclusion. Okay, and actually I have still some time, obviously, to address questions down the road. So we propose a machine learning-based measure of conservatism, differential timeliness. We have actually fewer economically anomalous observations. You saw that it was much more stable. We were able really to filter out at least the noise relatively to those other measures. And to push forward this MLC2 measure of machine learning, we don't need actually to even take into account the year fixed effect. We can achieve a better fit if we include those additional variables, because MLC2 is including for sure additional variables as well. But the machine learning also is incorporating the effects of non-linearities that are also pretty important in this approach. At the end, our measure is more robust to misspecification. We have seen that with the simulations. And to highlight again the advantages of using a neural network method, you can then get a better fit, you can reduce noise, and then you can also add restrictions. Again, Ayun, we are also working on the other specification where we relax those positivity restrictions, and maybe also we should do more about this H problem that is related to this positivity aspect of the co-movements between earnings and returns that maybe we should relax. So that is pretty much it. I wanted to thank everyone for all the feedback. At the end, if you are interested in using machine learning, so you can look at our paper and obviously the different tests that we have conducted. Again, we have the open source file that is available where you can get our MLC2 measure that you can use in your designs. And finally, also, Ayun, I think you were asking us to announce, the next event for ADP, which is coming on Thursday, April 21st, between 11 and 12, so Eastern time. And then the presenter will be Wu-Wang Zhao, and the paper will be about why has PEAD declined over time, increased arbitrage, or decreased earnings persistence. Okay. So post-earnings announcement drift.
Thank you for the great presentation. We still have 6 minutes. Are there any more questions for Edwige?
So I think, Mario, maybe because Ayun was really interested, maybe you could explain more about the neural network for the people that want to know more about, like the method itself.
So can you come back to the
Yes, it's
to
what
the
I was
equation?
about to, yes.
Like not even the neural network, to the equation. Yeah.
The equation.
Yeah, so
yeah.
I mean, I think the interesting part here is that you see that the functions f, g, c, and d are only a function of y, which are the firm's characteristics. The r and d are only used to have the breaks between good and bad news. So what we thought about, how can we use machine learning to get a measure that uses Cannon-Watt and Basu framework? You cannot just take it out of basic machine learning method and run it, because if you do that, you would have to include the R in the function that you estimate, the function M. So we thought hard about how can we extract this function C that would depend only on a firm characteristic, even if you estimate a function that has an R in the argument. And that's actually not possible. The only way that we could get at that is to get a neural network approach where we have these embedded networks, F, G, G plus C, and D, and have the R separately. Any other methods that we tried, even estimating the function separately and combining them, we have no convergence proof, like it doesn't work. So I thought that was an interesting way of thinking about the specificities of neural network. If you have a function that you want to estimate, whether it's to get a measure, whether, even if you do structural estimation or if you do other things, you can actually design a network just as you want it. And, pick these functions, design the network the way that you can estimate this function. And the nice thing here, you estimate everything at once. So, the way that you train that is by basically, gradient descent, like you just, optimize this, and everything is optimized at once. So I think that's a point that's interesting.
Which is here, correct? It's what happens.
Yeah. So you basically have this last circle here that gives you the earnings, and you feed the earnings, and all of these embedded functions are trained at the same time. So I thought that was maybe something interesting for people to understand. If you have any question on how that works, I can answer this in 3 minutes.
Thank you very much. Yeah, I think we still need more time to think about it. I speak for myself. Yeah, so we're gonna stop recording, but if anyone has more questions, welcome to kind of stay and